Hi everyone, welcome back to MATA02, the magic of numbers. I hope you guys are having a safe, warm, and quite snowy morning. Today, we're going to be talking about powers and roots. And so let's go ahead and get started. So we've now invented several different kinds of numbers, right? So we started off with just like the counting numbers, but then we started inventing a couple other numbers. There are several different reasons you might do this. For example, you might invent negative numbers so you can talk about financial debt. So how much do you owe to, say, for your student loans? And so these negative numbers make it easy to talk about financial debt. They make it easy to talk about when one person owes someone else or some amount of things, even if like negative numbers of apples don't really make sense. Well, we also invented some things for other practical reasons. So, for example, fractions, well, they let you measure smaller quantities of a theoretically continuous substance. So, like, if you have a length of rope, and you want to measure half of it, well, it's helpful to have fraction lists there because it lets you like cut it in half. It lets you divide things up. And there are some nice theoretical reasons. So like there are these practical reasons that you might want additional numbers, but there are also some theoretical reasons. One of which is that negative numbers mean that subtraction then always makes sense. You can always subtract if you have negative numbers. And fractions mean that almost all divisions have an answer. You still can't divide by 0, so 5 divided by 0 is still not allowed. But everything else is allowed. And so it gets you most of the way there. And so this sort of theoretical consistency is super useful for mathematicians because it lets you create these big sets of rules to explain what's going on. But now, of course, when we're talking about these different reasons to invent numbers, a large part of the reason is you have some operation you want to do to your numbers. For example, you might want to subtract things, and you want that to make sense. Or you may want to divide things and have that make sense. And those are the two of the major reasons why we've invented new numbers. Now, notably, we didn't have to invent new numbers for addition, right? And we didn't have to invent new numbers for multiplication, but we did for the reverses of those operations. And so we can think about that a little bit more. So, well, what's all this about inventing operations? So, well, in school, we learn about, oh, wait a moment. So we learn about things like constructing new operations by repeating something. So like repeated counting, well, that's just addition. Sorry, let's see. So if I have 3 boxes and then I add another 2 boxes, well, that's the same as saying I start with 3 and then I add 1, count twice more after 3. So count twice after 3. Okay, and that's basically why we've invented addition, because it makes repeatedly counting easier. You don't have to count them one by one anymore. You can just say, I'm going to count 5 more times, by which I mean add 5 to whatever our number was. And we can reverse this by subtraction. So, did that just do anything? Okay, good. So like 5 minus 3 is equal to 2. So you can reverse it by the subtraction operation, and of course that's where we get our negative numbers. That's where they become important. Now sometimes you want to subtract away more things than you have. Come on, what are you doing? There, okay. Of course, then we also have repeated addition. So that's multiplication, which you can reverse by division. And one way of seeing that is, let's suppose that we have 3 groups of 2 boxes. So 3 times 2 boxes. Well, what does that mean? So 3 times 2 is equal to 2 plus 2 plus 2. Or 3 plus 3, because it's also reversible. But we can think of this as 3 copies of 2 that we're adding together. And this gives us 6. And we can also reverse it, so 6 divided by 2 is equal to 6 over 2, which is equal to 3. And this is where we get fractions from. Okay, so that's all pretty easy. Well, now, as a mathematician, one of the things you might be thinking is, well, can we keep on going? So what if we repeat multiplication? Well, you guys have seen this before. So if you repeat multiplication, what you end up with is things called powers or exponents, exponentiation. So 2 cubed would be is our notation for 2 times 2 times 2. So instead of adding them all together, we're multiplying them all together. Again, we have 3 copies here, and that's equal to 8. And one thing you might ask is there a reversal operation to go from 8 to 2? And we'll get to this a little bit later, but we can define a reversal operation. We can define the root operation. So the cube root of 8 is equal to 2. But we'll get to that a little bit more later because there are some subtleties that happen there. So, now let's think a little bit like a mathematician. So in school, we learn about addition, multiplication, and exponentiation. Can we keep going? And so please put in chat, can we keep going? Okay, yeah, so that was in some ways a bit of a leading question. The answer is yes, we can keep going. Well, what does that mean? Well, what happens when you repeat exponentiation? Well, you can write it down like this. So maybe 2 to the 2 to the 2. And you can write, different people have different notations for this. So this is a little bit non-standard, but I'm going to use Donald Knuth's up arrow notation. So he used this notation with 2 arrows to mean something that we call tetration. Tetration. And you can even keep on going. So then repeated tetration is equal to something called pentation, and then you also get hexation. So that isn't casting a bad spell on someone. That's repeated pentation, etc. And of course, you can keep on going, and using the up arrow notation, you can just add more arrows if you want. But now, that of course raises the question, why don't we learn about these things in school? And I'll give you a couple options. They're too complicated, they're practically useless, or maybe you guys did, and I just don't remember, or maybe you guys don't remember. So, why don't we? Oh, wait, it seems like a lot of people did learn these in school, which is kind of cool. Okay, we have a good mix of things, so. Okay, yeah, so as a mathematician, you can define these operations. And there are a number of reasons, though, why we don't talk about things like tetration or pentation as much in our math classes. And there are several different reasons. And the big reason is that it's not actually that useful in most things in everyday life. And it's not completely useless. But it is pretty complicated, and it's not super useful to learn all these things. Which might then raise the question of why we stop at a particular point. So we had addition, multiplication, exponentiation. Tetration is very well defined, and you could do these, and there are a couple applications in computer science where you do make use of these the tetration operations, such as in but we don't really see it all that often, and so we don't really teach it that often in school. And I would be really curious, I'm a little bit surprised that so many people did learn this, but I guess maybe it's one of those things that when you learn about the other operations, you also be like, well, what if you keep on going? And that is something mathematicians ask all the time. What happens if you just keep on going? Now, okay, so why do we care about powers? And to answer this question, I'm going to have a couple of slightly unfair questions. Suppose you owe $10,000 in student debt, which grows at 10% a year. How much do you owe in 10 years if you don't pay it off? And yes, I know that this isn't a particularly fun question, but it is an important one. And questions like this are one of the reasons why we learn about math. Because for better or for worse, finances are a very important part of modern day life, and lots of weird things can happen. Okay, so we have a bunch of people who are, so we have a mix of answers. Some people think that so we're split basically between A and E. Okay, so we had some people chiming in with some B's, a D. Okay. Okay, it is good that most of you guys got this answer right. So, if you have $10,000 in debt, which grows at 10% a year, that means each year you're adding another 10% to it. What does that mean? So that means that if you start doing this, the answer is that you start with $10,000 and then you multiply it. Well, after 1 year, you multiply by 1.1 because it's adding 10% to it. But then the next year, you multiply it by another copy of 1.1, and so on. And you have 10 times this. So that's equal to 10,000 times 1.1 to the 10th power, which is about equal to $61,159. So note that this is a lot more than just 20,000, because even though, because if it grows at 10% each year, the 10% for interest rates at least applies to the total amount. So after 1 year, you owe 11,000, but then after 2 years, you owe 12,100, and so on, and that keeps on adding up. Which is one of the dangerous things about compound interest, of course. But on the other hand, if this is money you've saved and you're earning interest on it, then you get compound interest working for you instead of against you. Now, this is one of the major reasons why we want you guys to care about powers, is because it has a very real day-to-day impact on your life. Like, maybe it doesn't seem quite as real in some ways as, like, well, counting objects, like knowing how many apples you bought, or having pairs of items together and having multiplication, like figuring out things like areas or volumes. But it is still super important. There's another reason that's come up lately. So, I've given you, let's go ahead and talk about another reason that this is super important. Suppose that the number of people infected by COVID doubles every 3 days. If one person is infected today, approximately how many people are infected after a month? And let me reset before doing this. So what are people guessing? So people are guessing E just because it's a lot of people. One person guessed C, one person guessed D. Now remember, I've sort of told you like how to work these things out, right? So you use just powers. But, I mean, like, I think you'll agree that this has unfortunately become a very important part of our day-to-day life and influences a lot of our decisions. And of course, you can just wait for someone else to give you the number, but it's useful for you to have a sense of how quickly these things grow. Okay, so it looks like a lot of you have just answered E because it's a lot of people. But let's actually calculate this out and see what happens. So what does 30 days mean? So 30 days, if it doubles every 3 days, then so I'm going to say a month is 30 days just for ease of computation. So that means we have 30 divided by 3 equals 10 doublings. Okay? And if one person's infected today, times 10 doublings, so that's times 2 times 2 times 2, 10 times, that's equal to 1 times 2 to the 10th power. And 2 to the 10th power is actually 1024. So the answer here is actually C. Yeah, so it looks like a few people got that, but this is one of the reasons why you have to be a little bit careful with these sorts of numbers, because you can't just guess a number and then guess that it's going to be super, super big, because it isn't always super, super big, though in this case it's pretty bad. In fact, it turns out that it's even worse with Omicron, because Omicron seems to double every 2 to 3 days and not 3 days, whereas like the old variants seem to double every 3 days roughly. Okay, so I hope I have convinced you with these sort of not fun examples why powers and exponents are important. And this is one of the major reasons why we could talk about things like tetration, pentation, hexation, and so on, just all these other repeated operations. But there aren't really that many examples where you'll see those things used. And so for that reason, although like for some mathematicians and computer scientists, they get used occasionally, we don't talk about that so much in school, except as an example of these sorts of repeated operations. Okay, let's keep on going. Okay, so now going back to relationships to inventing numbers and operations, that's not quite enough. We also need to figure out how they relate to existing numbers and operations, right? So one big example of this, which you guys should hopefully know, is the distributive rule, where you relate together addition and multiplication. So if you add first and then multiply, what happens? Well, what happens is if you 2 times 5 plus x is going to be equal to 10 plus 2x. Because you multiply each individual thing in the parentheses, and that's equal to the original thing. And this is a rule that you can come up with that's based off of this sort of repeated operation, right? So multiplication is repeated addition, and so that's basically adding copies of each of the different parts of your addition as well. There are some subtle consequences. So you can come up with these rules just by looking at the like a bunch of boxes and sort of organizing them. But one of the things mathematicians do is, well, you come up with this rule and you're like, well, this rule is always true. But what other consequences do these have? And it turns out that one subtle consequence of the distributive rule is how to add fractions. So you guys all learned in school that if you have 1/3 plus 1/2, that's not equal to 2/5. So that's not true. And why is that? Well, let's draw it out in a pie diagram. So if I have a piece of pie and I cut it into, oh, I cannot draw. Let's try drawing a better dividing into 6. So if I have a pie and I want to divide it up into 6 pieces. So you don't want me cutting cake. I'm not very good at cutting even spaces. But yeah, so we've divided up into 6 pieces because what you might do is you might take this half plus a third, which is then 2 of the pieces. And so the answer is that this thing is actually equal to 5/6. But you might ask, well, why is that the case? Why is it equal to 5/6 and not 2/5? Well, the reason for that comes from the distributive rule. So if you have 1/3 plus 1/2, well, you can rewrite this using the multiplicative identity. So that's 1 times 1/3 plus 1 times 1/2. Okay? So that's not changing too much. But what you can do is then you can replace 1 by 2/2. So 1 is then 2/2 times 1/3. And replace the other one by 3/3 times 1/2. And that gives you, when you multiply, that gives you 2/6 plus 3/6. And now notably, this is equal to 2 times 1/6 plus 3 times 1/6. And then you can use the distributive rule to get you 2 plus 3 times 1/6, which is equal to 5 times 1/6, which is equal to 5/6. So how you add fractions, it's not some other rule that people made up when they made up fractions. It's just something that happens because of the distributive rule of multiplication and realizing that fractions are just multiplying by reciprocals. And when mathematicians analyze all these things, what they end up with is a lot of properties and theorems. So for each of these rules that mathematicians have taught you throughout the course of your schooling, it's because someone came up with one rule, and then people are like, well, if you have this one rule, what else happens? And it turns out that you don't actually have to learn about adding fractions separately if you know the distributive rule, and then you take the time to figure out, well, what are the other consequences? So if I know thing A, then I also know thing B. And because exponents are a little bit more complicated, I'm going to take some time and actually go through and work one by one through different properties of exponents, and I'm actually going to even prove some of them to you. So try not to be too scared. I'm not going to expect you to do proofs, well, not very often, and not yet, certainly. But you should start getting some of that flavor because proofs are a large part of how mathematicians think. And it's a sort of weird way of thinking because it's making use of things that we know, and then we're just like converting that into things that we don't know, but that we know must then be true. Do we have any questions about that? I know that some of that's a little bit sort of abstract, and I want to make sure I'm not confusing you all too much about that. Okay, so, I mean, let's go ahead and show some relatively simple proofs. Oh, what did you do on the right side there? There were a couple of, sorry, where do you mean that? So what we did here is we used the distributive property. So this here was the distributive property, where we used this property here to turn 2 times 1 over 6 plus 3 times 1 over 6 into 2 plus 3 times 1 over 6. Okay, so over on the, yeah, so that's sort of what I was saying. Like, this is a subtle consequence of the distributive property. It's not obvious initially that you can add fractions because of the distributive property. But when you're really, really careful about your reasoning, you figure out that, oh, adding fractions just is using the distributive property and factoring the 1/6 out. Okay, but now let's give our first proper proof of the class. There will be a few of these. Today we're going to spend a little bit of time on them just to show you that proofs aren't actually as scary as they look. So I'm going to write this big scary word, proof. Well, what is a proof? A proof is just an argument. It's just a logical chain of reasoning from step A to step Z and all the steps in between to show that if one thing is true, other things must be true. So I'm going to work only with integer powers. So let's say that m and n are positive integers. Just to make life a little bit easier. So they're like 1, 2, 3, 4, 5. The proof gets a little bit more complicated when you start dealing with things that aren't positive integers, but we're going to start with the easy version of this. So the first thing to do is notice that a to the x plus y, oh sorry, not x plus y, that's an m and an n. A to the m plus n, well, that's just saying that you're multiplying together a by itself times a m plus n times, right? So this is the reason we use integer powers, because then exponentiation is just multiplying by yourself, m plus n times. But we can group the multiplications together. We can group the multiplications together into the first m times and the next n times. Okay? So that means that a to the m plus n is equal to a times a dot 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 a, and this is m times a times a dot 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 another n times. Okay, let's write that out since that's a little bit abstract. What do we mean? We mean, well, if you had 2 to the 3 plus 4, that's just equal to 2 times 2 times 2 times 2 times 2 times 2 times 2, right? Because you have it 7 times. But you can say, well, let's do the first 3 times and the next 4 times. So 3 times and 4 times. And so your m and n are just any positive integer. So now once you've done that, then you can just use the definition of exponents. So, and by the definition of exponents, that means that a to the m plus n is equal to a to the m, because that's just multiplying together a by itself m times a to the n, because it's multiplying a by itself n times. Okay? And that's a proof. So what we started is we started with this definition of powers and exponents. And then we said, well, what happens when you have addition inside of the exponent? Well, the answer to that is the addition inside the exponent just turns into multiplying together, well, m times and m times and n times. Okay, so that was a proof. Did that make sense to people, roughly? So just a chain of arguing, just a chain of reasoning that if one thing is true, so if you have the definition of powers and exponents, this other thing here is also true. Okay, great. I don't see any confusing questions. And do we write? Ah, yes. Thank you very much for that question, Tristan. Do we write proofs in writing or with numbers only? So that's a question that comes up a lot, actually. So because one of the things you learn in you might have heard at some point is that like math is an entirely different language, right? And so that's probably what you sort of are getting at. Like, do you write it in the language of math or the language of English? And the thing is that to a professional mathematician like myself, there isn't a big difference between English and numbers. So everything I write down in numbers, that's just a short way of writing together things that you could write in English. So for example, saying this sentence here, but we can group together the multiplications together into the first m times and the next n times, and this equation there mean the same thing. And so I think it's bad to think about this like distinction between writing English and writing numbers. Numbers are a part of English, and math is just a shorthand for writing together lots of words into a very small space. So for example, those of you guys in when you're chatting on things, so I'm going to date myself a little bit now, but I might ask questions like, oh, are you going to type in chat using English or emojis? And of course, like you might be like, well, like emojis are part of the English language now, right? And so that's an argument some people might make. Like, well, like, yeah, emojis, they mean something different, but you use them as part of the English language. So you might use acronyms like LOL or ROFL or things like that. And so mathematical symbols fall into the same sort of category as like emojis or like acronyms. So when you're writing a proof, you're writing them in English, but you're writing them in English with these additional symbols that you can think of like emojis. Does that sort of answer your question, Tristan? Is there going to be a step-by-step on how to write a proof? Not yet, because so I wrote a proof, and I want you to be able to understand them, but writing proofs from scratch is kind of difficult. So it's like, and so I'm not going to ask you to do them on the first assignment or quiz. When I ask you to write things that are more proof-like, I will give you a step-by-step about very specific types of proofs. But the skill of learning mathematical proofs in general is actually quite hard, and something that even math majors and specialists struggle with. And so, like that's something that our math majors and specialists have trouble with up until like even until like C-level classes. Like they often still have problems with it. So for now, I just want you to try to understand them, to try to understand this kind of reasoning, and then maybe we will do some baby proofs a little bit later, but don't worry about it quite yet, Holly. Okay, but today I am going to show you some more proofs, because not full proofs, but sort of like the ideas behind the reasoning. So doing a fully rigorous mathematical proof takes a lot of careful thinking about special cases. But thinking mathematically and just reasoning through things, that's a little bit easier. Let's talk about exponents and subtraction. So it turns out that there's this rule, which you may have seen, that a to the m minus n is equal to a to the m over a to the n. So somehow you're now dividing, which sort of makes sense, right? Oh, sorry, for the top right example, would the proof be 2 to the 3 and 2 to the 4? Oh, yeah, so if I finish this off, this would be equal to 2 to the 3 times 2 to the 4. Exactly. Yep. And so that's a sort of argument you can make. So you're allowed to write these things down, even if you don't know this rule. So I'm giving you this rule here, but even if you didn't know this rule, you could prove it by using this argument. Okay, so now let's come up with a different rule. So I'm giving you this rule already, but of course people had to, one day, a very long time ago, people had to discover these rules. And then they figured it out, and then they proved it, and then in school, you may have just been given a list of a bunch of rules and been like, here, memorize all these things because other mathematicians have figured them out. And well, that's one of the things I'm trying to avoid a little bit in this class. I've been trying to show you that the sort of invention of numbers, like it's a process. It's not just like a set of facts that someone throws down at you from on high. I mean, it can be that, but that's not the sort of joy, that's not the beauty of mathematics. That's just someone else coming up with mathematics and forcing you to like memorize it. There will be some of that because there's a lot of mathematics and reinventing all of it is quite hard. But we're going to, at least in this class, try to give you a sense of how these things came about. Okay, so exponents and subtraction. Let's do the easy case first. So the easy case is going to be when x is greater than y and both are positive integers. Well, Len, we're going to start with the right-hand side first instead of the left-hand side. So what is a to the m over a to the n? Well, we can write this out pretty easily, right? So this means that we have a times a times a m times. So this is m times and a times a times a n times. Okay, and this is going to be a little bit weird to look at when you're doing it abstractly. But let's say that we had a concrete example, 2 to the 4 minus 2. Okay, so we want to show this is the same as 2 to the 4 over 2 to the 2. And the way we do this is, well, 2 to the 4, that's just, this thing is just equal to 2 times 2 times 2 times 2 over 2 times 2, right? But one of the things you may have learned is that when you have the same thing on the top and bottom, you can cancel them out. So those cancel out, and you're just left with 2 of them, right? So this happens to be equal to 2 to the 2. And we can do the same thing over here on the left. So we can cancel a bunch of these out. And what you're left with, let's cancel that one out as well. And what you're left with is you're left with, so let me write this in English. So we can cancel out n of the a's on top and bottom. And what are we left with? We're left with m minus n a's on top, which is equal to a to the m minus n. Okay, and so that proves this in this easy case. So now, in a rigorous math class, we would check all the other cases. So, for example, what happens if m is, someone should have called me out. I have an x and a y here. That should be m and n. So m and n. And hopefully I didn't use that anywhere else. In my notes, I used x and y for some reason and realized that I had gotten it wrong. So you're left with m minus n. Yeah. Okay, and so in the other case, you might check other cases, like what if n is greater than m? Well, what you end up with is you end up with more a's in the bottom, and then this formula still holds, but you just end up with 1 over, 2 to the third, or things like that. And then you might also check, well, what happens if m and n aren't integers? And that gets a lot more complicated when they're not whole numbers, because then you can't just use this argument of how many copies of things you have. But we're not going to deal with that. We're just going to deal with these easy cases where these are positive integers for the proofs. Okay, did that sort of make sense to everyone? This rule about exponents and subtraction comes out just from these definitions and from our understanding of what powers mean. And then we come up with this rule, and then we make you memorize it, but the rule came from somewhere. The rule came from this argument that we see here. Okay, so let's move on. What about negative exponents? Well, we already started thinking about this in terms of, so we could take the time to think about this in terms of just all the different definitions of exponents, but we can also use the rules we already have. So in this case, note that a to the m, let's start with n, actually. A to the n times a to the minus m Okay, what's that equal to? This is equal to the a to the n plus minus m, right? So that's something we already showed because that was our addition rule, right? So we already had this addition rule. If you have and then note that this is a to the n minus m, which we just showed was a to the n over a to the m. And so we didn't fully show that rule. We only show that rule when the top is bigger than the bottom, but we also showed that you could show this rule when the bottom is bigger. Well, then what does that mean? Well, this means that a to the minus m is equal to a to the 0 minus m, and so that's equal to a to the 0 over a to the m. And we'll see that a to the 0 is actually just 1 in a little bit. Actually, no, this is not how we're going to show it. We're going to show this a slightly different way. Sorry. So we have this, and then what do we do? Let's divide both sides by a to the n, right? So if you divide both sides by a to the n, you cancel out that, and you cancel out that. And so then what you get is a to the minus m is equal to 1 over a to the m. Okay, so that's a little bit more abstract of an argument because what we're doing here is we're making use of the rules we've already figured out and using them to imply this other rule. But really, and then what we have you memorize at the end of the day is something like 2 to the minus 3 is equal to 1 over 2 to the 3. And 2 to the 3 is just 1 over... Oh, you're having a hard time reading the green. Okay, I will switch away from using green for the important reading. Let me rewrite this. A to the minus m is equal to 1 over a to the m. Okay, I'll still use it for highlighting, but I'll try not to use it for the actual writing. Yep. Okay, so now we have a rule for negative exponents. When you have a negative exponent, it's just the reciprocal of the positive exponent version. And, well, I sort of hinted at this. Let's give a 0 exponent. So what happens when something goes to the 0 power? Well, a to the 0, well, you can rewrite this as a to the 1 minus 1. Which is equal to a to the 1 times a to the minus 1, which is equal to a over a, which is equal to 1. And note that it's important that isn't a minus m is equal to, isn't a minus m to the something equal to 1 over a to the m in the final answer? I don't quite understand your question, where the green text was. Ah! No, okay, so let me write it out in a little bit more detail. I made the mistake of skipping a step. So, we wrote all this out, right? And so we ended up with a to the m, a to the minus m is equal to a to the n over a to the m, right? So that's just the rule that's just one of our other rules, right? And so now what we're going to do is we're going to divide this by a to the n, and we're going to divide this by a to the n. Okay? And when you divide by a to the n, what happens is those things cancel out, right? So those things cancel out and those things cancel out. And so then you're just left with a to the minus m is equal to 1 over a to the m. So you have to be a little bit careful about the sort of reasoning that you do. And that's one of what makes proofs really hard, is because every single step you have to be very, very careful about applying your rules exactly, because if you do it slightly wrong, then your proof ends up wrong. Okay, but in this case, well, a to the 0 is just a to the 1 minus 1. And this is, look, the important thing is that this is only true when the a is not equal to 0. Because when a is equal to 0, well, then you have something like a divided with something divided by 0, which is not defined. And let me give a quick example. So let's say I gave you something super complicated. Log of 5,000 plus e to the 15 plus pi times sine of 30. But if I put that all to the 0 power, that's just equal to 1, so long as the thing inside isn't equal to 0. Sometimes you might hear, so like if you go on YouTube and ask like what's 0 to the 0, people will sometimes argue it's equal to 1. The answer is it's sometimes equal to 1 depending on what field you're talking about. Like that depends on what choice you make in inventing what it means to take powers. I personally think that 0 to the 0 ought to be equal to 1, but reasonable people will differ, and so we're not going to worry about things like 0 to the 0. Okay, and I am actually running out of time, but that's quite all right. If we run out of time, we'll just stop here and keep on going on Wednesday. So let's keep on going. So what we talked about there was we talked a little bit about where was I? Exponents and addition, right? So if you add together things in the exponents, that's equal to multiplying together the two different copies, right? What about the other way? So what happens if you take an exponent of an exponent? Then what ends up happening is you multiply together the exponents. And so let's see that. So if we have a to the y, I keep on using x and y because that's how I have it written in my prepared notes. So you should call me out immediately when I do that, so that I'm not confusing you guys. So a to the m to the n power. So what does that equal to? Well, let's look at the definition. Well, what that means is we take a to the m times a to the m times a bunch of a to the m's n times, right? So if we were to give a more complicated example, 2 to the 3 to the 4 is equal to 2 times 2 times 2. Oh, sorry, let me do this step by step. So this is 2 to the... Oh, sorry, I said I wouldn't use green. Go away, green. So 2 to the 3 to the 4. That's equal to 2 to the 3 times 2 to the 3 times 2 to the 3 times 2 to the 3. Because we have it 4 times, right? But then we can expand things out. So there are a couple of different ways you can expand them out. But the easiest is just realizing that that's the same as saying you have a to the m plus m n times. So that's also n times. Or equivalently, this is the same as saying this is equal to 2 to the 3 plus 3 plus 3 plus 3. But if we know that this is n times, well, that means that addition then goes into multiplication. So then this is equal to a to the m times n. Or likewise, this is equal to 2 to the 3 times 4. Okay? So you can apply this rule. So for example, if you have 3 to the 4, that's equal. There are several different ways you can apply this. One of them is you can apply it backwards. So 3 to the 4th power is equal to 3 squared squared, which is equal to 9 squared, which is equal to 81. Okay? So again, we have this rule. It comes out of all of our other definitions, and then you can just memorize this rule and apply it. So this is exponents and multiplication. You also have to be a little bit careful. Multiplication and exponents going the other way. Let's see. So 2 to the 3 times 4. Yes. Yep, exactly. So this is equal to 2 to the 12, which is equal to 4,096, I think. Yeah. Yes, that's right. Don't worry, I don't expect you to have that memorized. I just happen to know it. So. Okay, so now let's talk about multiplication and exponents. So note that what we had here was we had a to the m to the n. Here we have ab to the m. So if you have multiplication of the things that are inside that are under the exponent, what does that equal to? Well, that's equal to multiplying them out separately. And this is pretty easy to see because ab to the m is equal to a times b times a times b times a times b, and we have m times, right? If you have this m times, well, when you have multiplications, for a quiz test, will we have to memorize all these formulas? Yes, you will. That's not quite true. You can either memorize these formulas or you can rederive them. But yes, you will have to know these formulas. If you look at today's ungraded homeworks, as well as the first graded assignment, which are both posted online now. I have these formulas repeated, and yes, you do need to know these. So knowing these sorts of rules are the same as like knowing how to add fractions. Oh yeah, so let's see. Let me finish this and then I'll answer a couple questions about the assignment. So let me finish this section at least. So you have m times, well that's the same as a times a, m times b, m times. And that's using the commutative rule of multiplication, which is going to be equal to a to the m times b to the m. Oh, sorry. And let's give an example of that. So for example, 6 squared is equal to 2 times 3 squared, which is equal to 2 times 3 times 2 times 3, which is equal to 2 times 2 times 3 times 3, which is equal to 2 squared times 3 squared, which is equal to 4 times 9, which is equal to 36. And note that this is actually sort of similar to the distributive property. Oh, sorry, I overwrote something. Because repeated multiplication is repeated addition, and exponentiation is repeated multiplication. So this is basically the distributive property that relates exponents and multiplication together, as opposed to the distributive property that relates multiplication and addition. We had a question in the chat. In the assignment we were assigned on CrowdMark, due January 28, the homework assignments, yes, you're allowed to get help as long as you cite who helped us. Like, I encourage you to collaborate. Use the Discord group, use the Piazza. You should collaborate on the homework assignment, and I don't even mind if you collaborate with the entire class, so long as you write down where you got your help. You should be keep in mind, though, that there is a quiz the week after, and in the quiz the week after, I will probably ask you similar sorts of questions, and you will have to do that yourself. Okay, let's keep on going. I have a couple more minutes before, I think I can, yeah, I have a couple more minutes, and then we'll finish up for the day. Oh, okay, so we've only been talking about positive exponents. So what does it mean to have a fractional exponent? Well, you can think of these as roots. I mean, that's what they are. That's how we define them. And so what do we mean by that? So a to the 1/3 times a to the 1/3 times a to the 1/3 is equal to a to the 1/3 plus 1/3 plus 1/3, which is equal to a to the 1, which implies that a to the 1/3 is equal to the cube root of a cube root. This is also why you might sometimes see things like a to the 1/2 is equal to the square root of a. Because if you multiply together 2 copies of that, you get a. And if you multiply together 2 copies, that's adding together the 2 1/2 exponents. I'm not going to spend too much time on that. So a to the 1/3 is equal to 2, because that's the cube root. And by cube root, we mean 2 times 2 times 2 times 2 is equal to 8. So let's summarize up all of the exponent rules. So we have the rule that a to the 0 is equal to 1. So that's true so long as, so this is for a, b greater than 0, for positive a and b. We also have a to the m times n, a to the m to the nth power is equal to a to the m times n, or taking a power multiplies the exponents together. We also have this other rule, multiplying like powers adds the exponents. So note, this is only true if you have a in both of the bases. It does not work if, so for example, one thing that is not true is 2 to the 3, let's say 2 to the 4 times 3 to the 3 is not equal to 6 to the 7. That is wrong. Because you can't add them together if you're multiplying together different things. Negative exponents are reciprocals, and if ab to the m is equal to a to the m times b to the m. Okay? So let me give one example before, and I think I will then be out of time. So that's example 16 to the minus 4 1/4 times 3 squared is equal to 1 over 16 to the 1/4 power times 3 squared, which is equal to 3 squared over 16 to the 1/4 power, so the 4th root of 16, So that's equal to 9 over, well, the fourth root of 16 is the same as the square root of 16 times the square root of the square root of 16 and take the square root of that, equal to 9 over the square root of the square root of 16, which is equal to 9 over the square root of 4, which is equal to 9 over 2. And yeah, so I was going to finish up. I guess I'll do this next time for you guys to try it out. So if you look at the pre-lecture notes, I have these on there. And then, yeah, and I'll stop here because we are out of time. And then I'll finish up with the remaining 2 slides on Wednesday, at the start of the lecture on Wednesday. But yeah, so today we invented powers, and we also invented roots. And then we spent a lot of time really thinking about all these different operations and how these things relate together with addition and multiplication. So now, we didn't do this for the addition and multiplication section because, well, you guys already learned all those rules. And so we sort of sped past them. But we spent a little bit more time on figuring out what the rules are for exponents, and then now we have them listed out. So hopefully that gives you a bit more of the intuition of what exponents and powers are. And next time we'll talk a little bit more about that, and then we'll start going into things about specifically related to division. So we've almost finished inventing all the things that we're going to invent for now. Okay, thank you all very much, and I will see you on Wednesday.